Well, hello and welcome to Doc Onco Physics. Keith Onco here. What we want to do next is another torque problem, but it's slightly different. It's similar to the seesaw problem, but with this one, we're going to move the pivot point from the center of gravity of the seesaw all the way over to the left-hand edge of the board. So now we have a seesaw that, if left by itself, would simply tip down to the right in a clockwise fashion. Okay, but we have some other forces that are also going to be acting on our seesaw, and so our goal here is to figure out what force would have to be applied, a lifting force on the board. What force would have to be applied at the very end of the board itself to keep our seesaw in balance again, in rotational equilibrium. That's what we're really looking for, is how to keep our object in a rotational equilibrium. Okay, so we have the seesaw board itself, and the mass of the board is 100 kilograms, and that mass is going to act right at its center. I'm sorry, that force, the force due to gravity of the board, is going to act at the center of mass of our object. This is right at the center of the object. It's a uniform board. Okay, if we take 100 kilograms and we multiply by the acceleration due to gravity, all right, the force acting at that point is going to be 980 newtons. Okay, just to make it a little bit trickier, we're going to add another force that's going to be acting at about 0.25 meters from the pivot point, and that's going to be 320 newtons. So what we have is, we have two forces, right? We have the 320 newton force acting at 0.25 meters from the pivot point, or the center of rotation. We have a 980 newton force acting at 0.6 meters from the center of rotation. Okay, and those forces, right, are going to create torques. They're going to cause everything to go in a clockwise direction. Okay, so they're going to cause it to go clockwise. We need to figure out, right, what force needs to be applied at the end of the board in an upward direction to balance out the clockwise torque. So this is then going to be a counterclockwise torque. So we need to balance those out. Well, we know that we have the equation, the sum of the torques in the clockwise direction need to equal the sum of the torques in the counterclockwise direction in order for us to have rotational equilibrium. Right? Rotational equilibrium. Okay, and that's what we're striving for here. So let's see what we've got. Let's look at the clockwise forces first. What do we got? Well, we have 320 newtons. Okay, times 0.25 meters, that's the distance from the pivot point. Okay, so there is torque number one. We don't have to include the sine of the angle because all of these forces are acting perpendicular to the lever arm. Okay, this being the lever arm here, okay, the board. All right, so what other torques do we have? Well, we have the force of 980 newtons acting halfway down the board. So we've got 980 newtons, and that is acting at a distance of 0.6 meters from the pivot point, right? And those are the two torques that are acting, right, on our board, right? They are going to equal, so this is the clockwise torques, and we need to figure out now the counterclockwise torques that are going to have to balance that out. Well, we only have one force that's going to act in a counterclockwise direction. That's going to be F. And the distance from the pivot point is going to be 1.2 meters. All right. So now we have our equation. We have one equation. We have one unknown. We can simply solve for F. So let's see. 320 newtons times 0.25 meters is 80. Oops, that shouldn't be a point. That should just be 80. Let's get rid of that there. Newton meters. Okay. Let's go back there. All right. Plus 980 times 0.6 meters is 588 Newton meters. We add those up and we get 668 Newton meters is equal to F times 1.2 meters. Right? We divide each side by 1.2 meters and we get 556. So the force, whoops, is 556.7 newtons. That's how much of a force would have to be applied at the outer edge of the board to keep our board in rotational equilibrium. All right, so I hope that helps. We're going to be doing some more problems, especially ones in the rotational equilibrium sense. If you're still having trouble with these, take a look at those and I hope they help. Thanks for watching and have a great day.